So we have seen this. I apologize for the cutting of the previous recording. Oh, we are in this problem now. So water is flowing through a 3-inch pipe. The velocity of the water is 0.15 feet per second, and the kinematic viscosity is 1.924 10 times to the minus 5 feet per second. And I had mentioned that this was feet squared per second. So the Reynolds number equals velocity, diameter, density over viscosity, but this is the kinematic viscosity, so V d over nu, and the velocity is 0.15 feet per second. The diameter is 3 inches, so divided by 12, 1.924 times to the minus 5 feet squared over second. So this number here should give you about 1950 or 1949, the Reynolds number. So let's say you don't remember if that's laminar or not. Well, in your FE here, it tells you that it's laminar. So the answer to this is laminar flow. So all of these copies are from your FE manual. So the next problem is multiple choice again. We have pressure at point A and at point B, and assume there is no energy loss due to friction. So in point A we have, remember always to write the Bernoulli, and then if it has losses you include losses, but here it says no energy losses. So we have here Bernoulli plus Z2. Now, in this case, the pressure is 8 psi, and then the velocity here is 4.2 feet per second. The continuity expression tells me this is 2 feet per second. This here is 3 feet. This here is 10 feet. And then here is what we need to find out. Now, what's important here is that the units, remember, are very important in these problems because you need to make sure that your units are consistent. So you have here 8 pounds per square inch, but we need to have pounds per square foot, because if we have foot here, seconds, so we need pounds per square foot. So we need to convert this to square foot. So 1 square foot is 12 square inches. So this is 1152 pounds per square foot. And whenever we obtain this pressure, we'll also have it in pounds per square feet. And then whenever we look at the specific weight, you just look in the FE exam manual, and I think that I'm writing over it, but basically about 32 degrees Fahrenheit. I mean, this could have changed depending on what temperature you use, but we'll use 62.4. This is a specific weight. So I will then substitute this 1152 pounds per square foot. It's specific weight 62.42, and this is from your manual. The velocities are the same, so they will cancel, and then we have 10 feet. So remember, in this case, pounds, you have then feet, so the units are correct. And this tells me P2 over 60.42. I'm not going to write the units again because we have them. So then you solve for P2, and P2 should give you 1589.3. You can pause this recording and make sure that you do the calculations correct. But this is per square foot, so we need to convert that to PSI, or pounds per square inch, and we do the conversion. Now it's the opposite here in square, and this is 11.04 pounds per square inch, or 11.04 PSI. And so this is the closest value. So this question here, the water is flowing through a pipe and causes a pressure drop of 17,250 newtons per square meter in a 300 meter of horizontal cast iron pipe. And the question is, what is the friction factor? So let's write what is it that we have given. Of course, the temperature, the change in pressure is 17,250 newtons per square meters, and the length is 350 meters, and then it's cast iron pipe. We'll check on that in a moment. The diameter is 60 centimeters. So we need to calculate the friction factor. Now, just as a routine exercise, whenever we look at those 2 points, we have to do this. There's no pumps or anything, so we have V2 over gamma 2, V2 squared over 2G plus C2 plus the losses. The velocities cancel because they're the same. The elevations cancel because it's a horizontal pipe. So what I have is delta P over gamma. This is the same as my head loss. And at the same time, remember that the head loss equals, in this case, it's all losses due to friction. The friction factor L over D, B squared over 2G. Okay, but the question we have is how do we calculate the friction factor if we don't have the velocity, right? We have L, we have D, we have this, but then we have two unknowns, the friction factor and the velocity. So how do I calculate the friction factor? Well, the first thing is that it tells me that it's cast iron. So this is my roughness, and the roughness we'll do an average for the roughness. You can let me do that calculation. You can do it at the same time, and it would be 0.006, it's 3 zeros, 0.0006 plus 0.003, and that is 0.0018, but this is in feet. Okay, so this is in centimeters. So this is what you need to be aware of, that we need to make sure that you take into account that roughness. And I guess I'll have to just calculate it again here. So this is in feet, this is the average, and the diameter is 60 centimeters, which is 0.6 meters. So whenever I look at the E over D, or the roughness, the relative roughness, then I have 0.0018 feet divided by the diameter, but I need to convert it either these to meters or the feet, either feet to meters or meters to feet, and 1 meter 3.28 feet. So I have meters over meters, and this is 0.0549, and divided by 0.6, and this would be 0.0000915. Okay, so this is sort of approximately 0.0009, or depending how good you are at looking at the expressions, 10. So then you have to look at the Moody diagram, and I have marked it here, so it's somewhere here. And what I've done is, we assume turbulence, remember? That's one of the things we said in class. And so this would be my friction factor, approximately 0.02. Make sure you pause and understand what we're having here. So in this figure below, water is flowing in the pipe, and mercury that has a specific gravity of 13.6 is the manometer fluid. So we need to measure or determine the pressure in the pipe in psi, and then in inches of mercury. Okay, so if you look at your FE manual, you will find the necessary equations. So we need a specific weight of water, and we can assume, around 70 or 25 degrees Celsius, more or less. And then we have also here in your FE manual the conversion factors. So we'll use this, and then we have the conversion factors that we'll use in just a minute. And here is the equations, but let's first see it without equations so that we're reviewing the concepts that you need to understand. So let's assume here this is point O, and then this is 2. I'm using the same notation as in the FE manual so that you see where we are. So the pressure here, this is water. If it was air, it didn't matter where in that position. So what I have, P0, and I can go from left to right or right to left, equals P2, and then I go down, so I increase the pressure, plus, and then this is the fluid 2, which is the mercury, P2 plus, then gamma 2, H2, so I go to here, and then I go here, and then over there. So then I subtract, since I go up, minus gamma 1, H1. So we'll call this H2, and here this is H1. Okay? So this is one way to do it, and then if you look at the equation, these are the same expressions. So you had exactly what you had to do there. And so when I look at P2 is atmospheric pressure. So whether you did it including atmospheric pressure or just gauge pressure, as long as you indicate it correctly, should be okay. I prefer to eliminate numbers, so I just use gauge pressure. So I will say that the gauge pressure at O, which is what we're measuring in the pipe, equals gamma 2 H2 minus gamma 1 H1. So this is what we have here, and so you can use either this expression or the other expression. Now, as I mentioned, and maybe I'm going slower than I should, here I have the specific weight of water at that temperature. So let's say that I use 62.3. Okay, so if the density of water is 62 the specific weight, I should say, pounds per cubic feet, this is water, which is, we said we'll use the subscript 1. Now, gamma 2, which is the specific weight of mercury, is 13.6 times the density or the specific weight of water. In this case, we have specific weight. So this is 847.28 pounds per cubic feet that we have for mercury. Okay, so when I solve this expression, I will calculate the pressure, if it's gauge pressure. So I have pressure at point 0 is going to be equal to 47.28 pounds per cubic feet times 3 feet minus 62.3 pounds per cubic feet times 2 feet. And this should be equal to, is in pounds per square feet, 14.7. Let me do the calculation. So you can do the calculations with me here. I'm giving you time, 847.28 times 3 minus 62.3 times 2. It'll be something like 17.24 pounds per square foot. And the question was in PSI, so we need to convert that to pounds per square inch. So we have 12 square, oh no, I have it backwards. So remember, if you do a dimensional analysis and units don't cancel, that means that so we have 1 square inch. So .8 psi. And depending on the number or the density that you used, this can change. But now we have to do the conversion to inches of mercury, like I said. And if you look at the conversion, 1 atmosphere, you have it centimeters, so and 1 atmosphere equals also this. So we have, looking at those values, we have then 16.8 psi, and the conversion tells me that I have 1 atmosphere equals 14.7 psi, and also that's 29.92 inches of mercury. So 29.92 inches of mercury, 14.7 psi. So we have 14.2 divided by 14.7. I'm double checking all my calculations. So you should have 34 inches of mercury. So it should be something between 32 and 34. Okay. So I wanted to make sure you had this. Now this problem has a trick. You have 2 containers of water shown here, and the bottom areas are 2 by 2, the same water depth, so both of them have the same water depth of 10 meters. The L-shaped container, of course, has less water, but you're going to determine the hydrostatic force on the bottom of each container. And I have here pressure, but as long as you made it correctly. So what we're going to see is, we can have this specific weight, and this is in kilonewtons per cubic meters. So let me do it here. So the hydrostatic pressure is rho H. It says nothing about if it's thinner or if it's wider, and the pressure here at the bottom is going to be the same in both tanks. Okay, so what we have is the same pressure, and we have 9.777 kilonewtons per cubic meter times 10. So we have, I mean, you could have used 20 degrees. If you use 20 degrees, then it would be 97.89. So as long as I saw what temperature you used, so what we have is that the pressure, and let me go this way, is 97.7 kilonewtons per square meter. So what we have is 97,700 newtons per square meter, and if the bottom has a 2 by 2, the area is 4 square meters. Okay, so this 9,700 divided by 4, then remember that pressure is force divided by area, so pressure times area is force, so 97,700 times 4, 390,800 newtons. Okay, so if you want it in kilonewtons, then 390.8 kilonewtons, and for the second tank would be the same pressure. So there you go. You didn't have to do two calculations here. Okay, so now we have a horizontal commercial steel pipe, 1.5 inches in diameter. So let's write this given. Horizontal, that means that there's no change in elevation. Commercial steel pipe. And the diameter is 1.5 meters and carries 3.5 cubic meters per second, so you should know that that's Q, 3.5 cubic meters per second, units of volume over time. The temperature is 20 degrees Celsius. And so calculate, and this is where you have to read the instructions very carefully. Pressure drop per kilometer of length. Okay, assume minor losses are negligible and the friction factor is 0.011. So whenever we look, again, let me write, and I'm sorry to be redundant, but this is a good practice so you understand where things come from. There's no pipes and turbines. So you have gamma 2 plus V2 squared over 2G plus C2 plus the losses. So the continuity tells me velocity is the same, elevation is the same, so 8L equals delta P over gamma. Now, this then also equals my head losses, and so we have F L over D, B squared over 2G. Okay? Now, the question is the losses per unit length of pipe. So here's the length. So I'm going to calculate HF divided by the length of pipe and just substitute in the expression. So I have the friction factor, the velocity. Well, I need to calculate the velocity because it's the flow rate Q is 3.5 cubic meters per second, but then I have to divide by the area to obtain the velocity, and the area would be pi 1.5 squared over 4, so the velocity is 1.98 meters per second. So I'm continuing substituted here 1.98 meters per second. This is squared divided by 2 times 9.81 meters per second square. So those both cancel. And what I have here is then my head losses are 0.001465 meters of head loss per meter of pipe. But it's asking for a kilometer of pipe. So I need to do this. And so here I have 1.47 meters of head loss per kilometer of pipe. So that's the answer for that problem. I'm doing this one because this one's kind of straightforward. I mean, and you calculated it in other problems, but water sprays through a 6-inch diameter. So this is 0.5 foot. The flow rate is 2.75 cubic feet per second. And so we want the velocity, and the velocity is Q over 8, and 2.75 cubic feet per second divided by 0.5 squared over 4, so the velocity is 4.0 feet per second. So this problem, we did one very similar in class, and this is one of the long problems. So the elevation difference between two reservoirs that are 2,000 meters apart is 20 meters, and you have a 30 centimeter commercial steel pipe. Here you have the coefficient for Hazen-Williams, 140. Pipeline connects to the reservoirs. The computed flow rate using Hazen-Williams equation is 0.136 cubic meters per second. So we'll determine the flow rate using the Manning equation, and I'm giving you the coefficients for Manning, Darcy Weisbach. So I'm giving you the roughness for that, and we'll have to calculate. Now, as review, this is the Hazen-Williams equation that you can find in the FE, so I've just copied and pasted, so you see that you had all this information. And this is just another way of presenting Hazen-Williams. This is Manning, and this is Darcy-Weisbach. And because we're talking about pipes, the hydraulic radius is the diameter divided by 4. Okay, so I should have left a blank slide here. Let me do that so we can keep it, and I'm just going to try and leave a, I guess I can't. So let me see how we can do this. There's light. So I hope that that works. Okay, so remember that the first thing we always do is sort of obtain the energy equation. So, oops. So P1 over gamma 1 plus V1 squared over 2G plus C1. There's no pumps or anything that adds energy. P2 over gamma 2 plus V2 squared over 2G plus C2 plus the losses. Okay? So it's two reservoirs open to the atmosphere. The pressures cancel. The velocities cancel. So this change in elevation is the head losses, and this is 20 meters. So when I look at Manning, and let me make sure I have here, this is a 30 centimeter commercial steel and 140 for Hazen-Williams, and then for Manning, commercial steel N equals 0.03. So let's do Manning first. So when I do Manning, what I have is V equals 1 over N, because it's metric, the hydraulic radius 2/3, and the slope 2.5. The slope, then what we have is 20 meters in 2,000 meters, and this is 0.01 meter per meter. The hydraulic radius is d over 4, which is 0.3 divided by 4. This is 0.075. So the velocity would be 1 over 0.013, 0.075 to the 2/3, and 0.01 here. So my velocity is 1.368 meters per second. And then of course the flow rate is V times the area, and so we have 1.368 meters per second, and then the area pi 3 squared over 4 is 0.7 0.071 meters squared. So I substitute here meters squared, and this is 0.097 cubic meters per second using Mani. Now for Darcy, and let me insert another slide, and we'll do that Darcy separate. So for Darcy, oops, remember we have HF equals F L over D, V squared over 2D. So we can solve for the velocity using Darcy, and this is one of the ways. HF D 2G. Okay, so we need to find the friction factor, and to find the friction factor we have, and this will simplify, okay, 0.045 millimeters, and then the diameter is 0.3 meters or 300 millimeters, so E over D is 0.00015, and if I assume turbulent, the friction factor, and we need to look at your Darcy diagram, should be 0.0125. Okay, and I have it here. So this is my E over D, and if you assume turbulent, then you can go straight to this point. Now, I wanted to comment on something. So now we have the 20 meters, which was the head loss, 0.3 meters diameter, 29.81. Remember, this is meters, meters per second square. The friction factor is 0.0125, and the length, which was 2,000 meters. So you'll have meters. Okay. So this will give me 0.686 meters per second. Now in practice, we would want to redo this. Now you can calculate the Reynolds number and prove that it's turbulent. But in class, I told you let's just leave it at that. So now with that velocity, we'll calculate the flow rate, which is 0.686 meters per second, and 0.0071 meters squared, and this is 0.049 cubic meters per second. So that's the problem. Okay, you have this, so make sure you review it. Now this is the problem that has the system of pipes, and you have to be very careful about reading it. This problem is from the book, different numbers, but one of the suggested problems for you to practice on. So what I want to do is go over, let's read it first. So in this pipe system, we have, that is here depicted, you have discharge from pipe cube AB. So this is the discharge. And then it tells you that this here has been substituted by a pipe that is 222 meters, 3 meters diameter, and the friction factor. And then this pipe here, CF, has a length of 400 meters, a diameter of 3 meters, and a friction factor. So you need to determine the length and head loss of an equivalent pipe with diameter of 3 meters and friction 0.1 to replace the system of pipes. So what I want to do is redraw this system. Okay, so I'm going to do this. Okay, so here we have point A, we have point B, point C, point F. Okay, so this pipe here has a Q of 100 cubic meters per second, has a length of 500 meters, the diameter is 2 meters, which means that the area is equal to pi. So then pi 2 squared over 4, so this is pi 3.14 meters squared. The friction factor is 0.018, and since I have the flow rate and the area, then the velocity is 100, so it's 31.8 meters per second. Now this was a branch, right? But it tells you already that this branch has been substituted by a length of 222 meters, diameter is 3 meters, friction factor is 0.02, area is pi 3.4, so the area then is 7.07 meters squared, and so therefore the velocity is 14.1 meters per second. Then for this segment, the length is 400 meters, the diameter is 3 meters, F is 0.02, so therefore the area is 7.069, and then the velocity is the same, 14.1 meters per second. So now we're going to calculate an equivalent length and the total head loss. So this is pipes in series, right? So in series, remember that then the head loss from A to F would be the head loss from A to B plus the head loss from B to C plus the head loss from C to F. The Q by continuity from A to B is equal to the Q from B to C and the flow from C to F. And you saw that in one of the homeworks. And they're telling us that for this pipe the diameter is going to be 3 meters and already gives us a friction factor of 0.02, which, in real life that doesn't happen, but so what we have to do is to calculate the head losses for each one here. So using Darcy, which is here, so the head loss here from A to B is going to be equal to 0.018 500 over 231.8 squared over 29.8, and this is 224.7 meters of head loss. I do the same here, and I'm going to just substitute, and make sure you pause and make sure you understand where the numbers come from. 0.02, 222, 31, 14.1 squared, 29.81, and this here is 14.99 meters. And then the one here would be 0.02, 400 over 3, 4.1 squared to 9.81, and so the head loss here is 27.02. So the total head loss from A to F would be the summation of this 3224.7 plus 14.99, or 15, right? 2702, and this equals 267 meters. Now, how do we get the equivalent length? Well, we can use again Darcy. And using Darcy, then we say the head loss is 267 meters equals the friction factor, because it was given 0.02, and then the length is what you're going to calculate. The diameter was given, which was 3. The velocity is the same as we have 3 meters so of diameter, so if you have the flow rate already given, it's the same flow rate, and for a diameter of 3 meters, then the velocity is 14.1 squared over 2 times 9.81. So we'll solve for the length, and the length, I'm not sure I have that calculation, so we can do it. Oh, I have it here. So make sure you have this, and so it's 3952 meters. So that's the answer. So that's the exam, with a lot of detail, maybe more than you need, but I hope this helps. Thank you.